All right, all right, all right. So today we're going to solve problem. What problem are we solving today? We're solving problem 1702, 1702, maximum binary string after change. Okay, so what does the title reveal about the problem? Well, we're dealing with some sort of binary number probably, and we're changing things. So we're modifying things. Okay, so we're doing something greedy, or we're doing something, DP, who knows? But we're definitely doing some sort of modification to make a binary number larger or smaller or meet some condition. Okay, so let's just go ahead and get started with the description. You are given a binary string binary consisting of only zeros and ones. Okay, that's common, right? If it's binary, it's going to be 0 and 1. And you can apply each of the following operations any number of times. Okay, so operation 1. If the number contains the substring 0, 0, you can replace it with 1, 0. So for example here, right, we have 0, 0, 1, 0. Now this is a string representation of it. And this is basically saying you can change any 0, 0 to 1, 0. So I can take these two 0, 0s and turn them into 1, 0. What the heck am I doing? And turn those into, take the 0, 0 and turn it into 1, 0. Right? So that's what happened here. Took the 0, 0, made it 1, 0. Okay, simple enough. And you can take any of the substrings 1, 0 and you can replace it with 0, 1. Okay, so for example, if you have this string here, you can take any 1, 0 and turn it into 0, 1. So I can take these two, right? I can take any 1, 0 and turn it into 0, 1. All right, so it's kind of simple operations that I can do. So I can take a 0, 0 and I can turn it to 1, 0. What's kind of weird about this is that you get 0, 0, 1, 0, and you can take 1, 0 into 0, 1. So technically you could take a 0, 0 and turn it into 0, 1. And I don't know if that really helps us that much, but it is true, right? Because you can take the 0, 0 and turn it to 1, 0, and then take that 1, 0 and turn it to 0, 1, right? That's going to take two operations, but you can get from 0, 0 to 0, 1, which is, I guess, could be helpful. All right, we want to return the maximum binary string you can obtain after any number of operations. Okay, so it doesn't matter the number of operations. We're just going to take this initial string that we're given and we're going to make it as large as possible. What does it mean for it to be as large as possible? Well, a binary string x is greater than a binary string y if x's decimal representation is greater than y's decimal representation. All right, I'm going to try to assume that you already know what a binary representation of a number is, right? I'd argue that you probably shouldn't approach any medium problem until you understand what that is, right? Because that's one of the very, early on learned fundamental topics of computer science. So you should probably, right, assume that you understand what that is. But just to make it, just to say it really bluntly, right? When you have a binary number, right, what you're doing is you're taking the number and you're saying this is, I'm going to go very quickly over this, okay? 2 to the 0 power, 2 to the 1 power, going all the way to the left. So it's a binary representation. That might be super confusing. All I'm saying is you want the most left elements to be 1. And after that, you want the most elements to be 1. Because the farther left you go in a binary string, right, the larger decimal number that represents, right, the larger power, right? Because like this, for example, is 16. Because this is 1, 2, 4, I can't even do simple. 1, 2, 4, 8, 16, right? And this is 15. Because the farther left you go, the larger the ones you get. The farther left the ones are, the bigger number it equates to, okay? So that's just one thing to remember here, right? You want to get as far left to be ones, right? And you want there to be as many ones as possible. Because every time there's a 1, that adds another number. If it's a 0, it doesn't add that associated 2 to that ith index, 2 to the index 1. I'm very just hand wavy going over this because I'm assuming you already know, but we're trying to make as left as possible 1, and we're trying to also get, if we can't get more left ones, we want to get as many ones as possible. Okay, so that's how we maximize the number, right? We want to find the largest number that we can get, and the only way we can do that is by kind of modifying the binary string by applying these two operations, right? Now, one thing is as well, how are we going to do this, right? And that's where this problem gets kind of difficult because it's not super clear how you do this. And the only reason I was able to solve this was by just making a huge example and kind of just like messing around with it and applying the operations and be like, how can I make this thing as big as possible? Then taking that information and trying to programmatically apply that to this problem, okay? So this is definitely one of those problems where it's very valuable. In most cases, it's very valuable to do the example, look at the operations that occurred, and see if you can infer anything about, okay, what's like the best approach to do this, right? And there's really nothing else to this problem, at least that I can explain. It's literally just look at the problem, walk through the steps to try to find the optimal, and see if that can be, you know, codified, right? Can that be stated in a manner that represents what is necessary to make this binary string optimal using the operations that are provided, okay? So, with that said, let's look at this example, okay? So, I'm actually going to do it independently, and I'm going to try to make this thing as large as possible, right? And again, remember, to make it as large as possible is we want to make everything to the left as possible ones, right? So, what operations do I have here? I have 0, 0, and I can make 0, 0, 1, 0, and I can make 1, 0, 0, 1. All right. Now, when I first looked at this problem, one thing I said is, well, maybe I never want to apply this operation, right? Because this makes the string smaller, right? Because remember I said that I want to make as far left. I want to make everything as far left as possible ones. So I might only want to do this, right? I might want to be like, I just want to make this 0, 0, 1. So I'll take this 0, 0, using that approach, right, I'd say, I never want to turn 1, 0 to 0, 1 because that only makes it smaller, right? I want to keep the ones as far left as possible. So why would I ever take 1, 0, make it 0, 1? Now I'm moving a 1 to the right. I don't want to do that. I want to keep all the ones as far left as possible. So let's just disregard this for now and say, okay, that seems logical. Now, just, you know, what's the word I'm looking for here? Right, spoiler alert. That's not what we're going to do. This operation actually does help us, but I guess my poor intuition tells me that this is making 0, 0 into 1, 0. So it's adding ones to the left. It's making it bigger. That's good. I should only apply that. This thing, on the other hand, is making it smaller. So why would I want to do that? Just ignore that. But we'll see what happens when we use that logic. Okay, so if we use that logic, well, what could we do? We could turn this 0, 0 to 1, 0. And then 0, 0, 0. Now the thing that happens here though is now that, okay, we started here. Then we could turn this 0, 0 to 1, 0. And then we'd say, okay, well, we're done, right? There's nothing else we can do. We've made this as large as possible using only this operation, right? But then when we look at the actual final answer, the final answer is bigger, right? Because although they're the same in the first two, the final answer was able to get this one a 1, right? And only this one maintained being, in our version of only using that first operation, it's smaller. So how the heck is applying this operation, which makes it smaller, end up making it bigger in the end, okay? And let's think about how that works, okay? So what do we have to do to our answer here, where we use this approach of literally just making 0, 0, 1, 0 into 1, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0. Right? How do we get from here using only the first operation to the actual final answer where it's actually bigger? Well, this operation is just a bit shift to the right. Right? We take a 1, 0, we make it a 0, 1. So we can actually, you can think about it as just moving that 1 over places, right? If I had this string, for example, right? If using just this bit shift operation, I could do 0, 1, and then I would apply it here, 0, 0, 1, 0, 0, 1. And what am I doing here? Well, I'm just applying it every time I see this 1, 0. I'm making this 1, 0 into 0, 1. Next operation, I see this 1, 0, I turn it into 0, 1. See this 1, 0, I turn it into 0, 1. See this 1, 0, 0, 1, right? So I can take some 1 all the way to the left and I can roll it all the way over. All right, now what would be the benefit of doing that? Well, in our example here, we can see that we can make it bigger. Right? We can make it bigger by making this one bigger. Making this 0 into a 1. 0, 1, 0, 1. That's probably a very confusing explanation. So what I can do is if I can make space for that by taking this 1, 0, making it 0, 1, 1, 1, 0, make this 1, 0, 0, 1, and now I have 2 zeros in a row, so I can apply that other operation to make that 1. Okay? Now what I'm basically saying here, right, is if I have 0 and a 1 here, maybe it's 1's forever and a 0 here. This is bigger. This is bigger than this. Right? So what's basically happening here is if I just move all the 1's over, I get another 0, so I can have that 0, 0 and make it 1, 0. Okay? So basically what I'm saying here is if I have this right here, right? If I shift all these over by making this 1, 0, 1, now I have another 10, 0, 1, right? I can always shift if there's a 0 in the spot. Then I can shift them all over until I get this. Right? And then I can take these 0, 0 and turn to 1, 0. All right, so how does this work? How does this solution work, okay? If you're given a string like this, for example, I'm going to do something crazy long here just to prove a point, okay? And this is what I actually solved to figure out what the optimal solution was, okay? First thing is that all of these 1's are already good. They're already good because they're all 1's. It's as big as they can possibly get, all right? So I can't change it first because there's no operation to change it, right? I can't change. All I can do is change 0, 0 to 1, 0 and 1, 0 to 0, 1. So I can't even do anything to these anyways, right? The first place I should try to think about how am I going to make this thing bigger is this 0, okay? Now the only way I can make this 0 bigger is if there's a 0 next to it, right? This is the largest thing. If I make this 0 a 1, it's greater than making all of these a 1 together, right? This is larger than this, right, in binary representation. So my focus here is making this 0 a 1, independent of what happens to its right, okay? So if I want to make this 0 into a 1, then I need to make this 1 here into a 0. Since there's zeros to the right here, there's space to shift, right? So I could shift all of these 1's all the way over by applying this operation. So in the end, you would get, and then I can make this 0 into a 1, 0. But then I actually have more operations I can do, right? I can take this 0 and turn to 1, 0. I can take this 0, 0, make it 1, 0, 0, 0, 1, 0, 0, 1, 0. Now I'm stuck with 0, 1 again, okay? So then I could shift all these 1's over until it faces more 1's. And now I have, okay, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0. Now I have the 0 again, right? I think you see where this is going now. So then I need to shift all these 1's over. Then I have 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0. And then, what can I do now? Well, I want to make this thing into a 1, but I can't because there's nothing to shift the 1's to. But if you look at all of these 1's here, when I started here, that's just all of these That's just all of these ones to the right anyways, okay? What I'm saying is to get to this point, that's the same thing as doing the following, okay? So remember, we ignore all these ones. Now, how many zeros are there to the left here? There's these ones, these ones, these ones, these ones. And those are going to get shifted all the way to the right. So everything else is a 0. And then, so because I can just shift everything right. I can shift all these ones to the right. Then I can shift all these ones to the right. Then I can shift all these ones to the right. And then all these ones to the right. It's the same thing. And then I can apply the operation of turning 0 zeros to 1 0. So 0 0 1 0, 0 0 1 0, 0 0 1 0, 0 0 1 0, 0 0 1 0, 0. And look at that. It's the same exact string. Okay, so I can always turn this freaking string into this thing, where it's all ones and then just 1 0. And how did I do that? Well, all I have to do is first I need to locate the first 0. Then I need to account for, after the first 0, how many ones will get shifted to the left, to the right. Then I can make everything, I can shift all those ones to the right. The very next thing has to be 0, because there's a 0, right? I can never make it all ones, because only thing I can do is turn 0 0 1 0 1 0 0 1. And then everything else is ones. Okay, does that make sense what I'm doing here, right? And that's what's weird about this, right? Because I didn't do any proof. I just solved the problem and then thought about, okay, what I'm going to do is I'm going to shift all the ones to the right. Right? Let's start over. I'm going to locate the first 0 because everything to the left is 1 and already perfect. Can you see what I'm writing right now? Nope. Messed that up. And already perfect. Right? Everything to the left here is already perfect of this 0. Okay? And then what I'm going to do is I'm going to say, well, when I shift everything to the right, I'm going to get only the ones left. So all these ones go to the right. So that's equivalent to saying, let's just put all the zeros where they need to be. It's the same way, right? So I'm going to shift all the ones to the right because I can do that by doing this operation. Because that's going to maximize the certain things that I can make 1. And then I'm going to just convert everything into 1 up into that point. So how many ones are there? There's this many ones, right? And you'll notice that all these can be made 1 0 1 0 1 0 1 0 1 0 1 0 1 0 all the way down the line, 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 all the way until this endpoint where it can't happen. So my answer is pretty much, well, the first elements before 0 are all going to be 1. Then there's going to be some unknown space of 1s, right? And then there's going to be 1s that are all 1s. And there's going to be a 0 in between. Like this. Okay? So how does that work? So let's just try to build it out. So before we try to figure out exactly how this formula works and if that makes sense, let's actually try to figure out how we can locate the zeros and the ones. All right, so we'll say 0 equals -1, and we'll look at each index. So we'll look at the whole range, and we're trying to find the first 0 in this system, okay? And we're going to say, okay, if binary at I at this index equals 0 and 0 still equals -1, well, then we'll set 0 to this index. So that'll represent the first place that we found a 0, right? Because as soon as we find a 0, it'll get set, so then this won't be true anymore. So it'll only set it the first time we see it, right? And then we'll say, well, also, if 0 doesn't equal -1, we want to count how many 1s we've seen, right? Because It's the ones that are to the right of this first 0 that we're going to shift all the way over so that we can start packing in 1s as much as we possibly can. So if 0 is not equal to -1, then we've set it. And binary of I equals 1. We'll say 1s plus equal 1. 1s equals 0. So we're basically saying find the first 0. And as soon as you find the first 0, start accounting for all the ones that are to your right. All right, now, for whatever reason, it's easier for me to build this string backwards. Okay, so we're going to build this string now. Now, like I said, we're moving all the ones to the right. Okay, so I'm going to build this string backwards, but you're going to see what I mean. So maybe we're given this. And then the first thing we're going to do is we're going to say, okay, here's our return string res. The first element's going to be a 1, and how many 1s are there going to be? Well, we moved all the 1s to the right, correct? So there's going to be 1s of those, okay? So if I was building this string from here, pretty much what I'm saying here is I just built this first portion here. So this is the final string. Maybe remember I'm building in reverse here. So this would be those first 1s. And then remember that other element always becomes a 0. Well, there's one special case where it doesn't. We'll face that in a second. But that first element always becomes a 0, right? Because that's the only one you can't pack, right? That's how it always worked out. We started here. We move everything to the right, right? We move everything to the right, and then we notice that we can move everything to the right, and then this thing becomes a 0 when we just pack through those operations. All right, so then the next element is going to be a 0. All right, so this element becomes a 0. So then how many elements become a 1 after? Well, it's going to be 1 again, but how many? Well, this is the location of 0. So if it was here, it'd be 0. 1. Okay, so this is one where let's just do 0. All right, now, remember, this is in reverse because this would put the 1s here. So then that becomes a 0, and then what's remaining at the location of 0 becomes a 1, like that. But this is actually in reverse, right? Because the 0 up into the position of 0's first, plus our 0, and then the remainders are 1 times 1s. So if we return that, we should be good to go. Okay. This might be 1 off. Zero is not equal to -1. Okay. Why did I put -1 here? Of I, sorry. All right, so let's print 0 and 1s here to make sure everything makes sense here. Right, because we're going to do the same thing here. 0, 0, 0, 1, 1, 0. So what was the operation here? Well, shift all the 1s to the left, to the right. And then you can make everything here into 1s with 1, 0 there, which is the final answer here. But we have some issue where it's not getting the first 1s. Because that's not actually... Okay, so let's figure out this equation here. Maybe it doesn't rely on 0. So we have the length of the string, right? The length of binary, which equals some value x, which is the number of 1s to the left. So we'll say that's the 1s to the left, 1s on the left, plus 1, because there's 1, 0, plus the numbers of 1s after. So then that means 1s on the left equals left of binary. I'm trying to figure out how many 1s are on the left here, right? Equals length of binary minus 1 minus 1s. So if we do that in terms of that, maybe we'll get... because Because we know all of them on the left are going to be 1, but how many are there? Well, turns out to be that. Now, this is probably going to be wrong because there's an edge case unless I don't understand the conditions, which is possible. So with 1, 1, right, it's already perfect. We don't need to do anything. And that would happen if there's no zeros. If there's no zeros, then there's nothing to shift or change. It's already how it should be, right? So we don't need to be playing this game. So if we do this and 0 is still -1, that basically means that, what does that mean? That means that we didn't find a 0. If we found no 0, it's all 1s. If it's all 1s, then it's already as big as it possibly can be, so we just return it as it is. Okay, so what is the run and space complexity of this? Okay, so let's say n is the length of binary. For time, we have to look at all of the characters. So we look at all n bits, I guess, of this binary string. And we have to rebuild the binary string the same length. So that takes O(n) operations, O(n) operations. So that's O(n) time, right? We do n operations. We do 2 constant things. We just check and see. We add to a variable. This all constant operations. So n constant operations. It's a constant operation. This takes n time to build. Okay. For space, well, we have to create this n length string in the end, right? We create these 2 constant variables. They don't grow with the size of n, but then we have to return n elements, right? So we have to create that string, so that's O of n space. All right, guys. Later, players.